Hey everyone, and welcome to this DEX 1084 Explainer. Whether you're studying mechanical, civil, or industrial engineering, today we're bridging that absolutely critical gap between textbook math and real-world industrial maintenance. We are taking the fundamental concepts of engineering statics, the exact same forces that govern jet flight paths and massive industrial crane operations, and we're breaking them down step by step. Our goal? Let's master the mechanics of moments so you not only crush your final examinations, but truly understand the massive structures you're going to design in your careers.
Okay, let's map out our tutorial for today. We'll start off by defining force moments, move right into real-world levers, calculate some 3D moments, test your knowledge with a quick quiz, and wrap the whole thing up with exam tips. Let's jump in.
Section 1, Defining Force Moments.
So a moment is strictly about the twist, right? It's a measure of a body's tendency to rotate about a specific axis. Think of a bobsled or a toboggan taking a really sharp corner on an icy track. The forces applied there don't just push it forward, they actually torque and twist it around the curve. If the body starts to twist or turn, you are definitely dealing with a moment.
Now, spatial alignment matters immensely, especially when we talk about things like industrial maintenance. For that rotational twist to actually happen, your applied force has to act at a distance. If your line of force passes dead center, directly through the exact centroid of, say, a structural steel beam, you get zero rotation. Hitting that exact center of gravity means the object is just going to push forward. It won't spin at all.
Let's lock these core definitions in right now, because they are literally the foundation for everything we calculate next. Remember, moments cause rotation, they are completely different from linear translation, and that force vector must deliberately bypass the centroid.
Moving on to Section 2, Real-World Application with Levers.
This perfectly illustrates a universal statics principle. Maximizing your distance drastically minimizes your required force. Imagine trying to lift a 20-kilogram mass by applying force right near a hinge. That requires two hands and maximum effort. But when you apply that exact same force far out at the end of a long lever, say 2 meters away instead of 0.2 meters, you drastically multiply your mechanical advantage. Suddenly, you can lift that heavy 20 kilograms with just a single finger. The mass didn't change at all, but your distance did.
By tweaking those distances, you achieve perfect equilibrium. Basically, a system is balanced when clockwise moments perfectly cancel out anti-clockwise moments. Let's do the math real quick. Since a moment is just force multiplied by distance, a 500 Newton force acting 1 meter away perfectly balances a 100 Newton force acting 5 meters away. You're literally letting the math do the heavy lifting for you.
Keep this very tangible physical behavior in the back of your mind as we transition our thinking into complex mathematical geometries. Increasing distance reduces the required force. The calculation is force times distance. And equilibrium means opposing forces perfectly cancel each other out.
All right, Section 3, Calculating 3D Moments.
Building directly on our Chapter 2 fundamentals, let's tackle sample problem 3.2.1. Picture a 3D structural cube in your mind. Out in the real world, forces rarely operate neatly on a flat piece of paper. Just think of the complex multidirectional forces acting on a jet's flight path. In this scenario, force vector P acts along the diagonal of one face. Your challenge is determining the moment of that force about edge AB, and then about the diagonal AG, by visualizing the geometry in 3D space. So here's your analytical strategy for calculations. Step 1. Establish your Cartesian vector equations by assigning your I, J, and K components. Step 2. Write out the expression for the moment about diagonal AG using a dot product. Step 3. Use that scalar result to mathematically extract the exact perpendicular distance. You aren't just blindly guessing the geometry here, you're systematically letting the cross products and dot products calculate those exact 3D distances for you.
That breakdown is exactly the systematic procedure you're going to need to rapidly execute on your final exams. Map it out in 3D space, pick your Cartesian vectors, and extract the perpendicular distances mathematically. Don't try to guess the geometry. Always trust the equations.
Time for Section 4, our Knowledge Check Quiz.
To make sure these concepts are really sticking for your exam, let's look at the ultimate master trick question that professors absolutely love to ask. If a massive force acts on a structural body, but the line of action shoots straight through the exact center of gravity, the centroid, what is the resulting moment? Well, the answer is zero moment. Without that perpendicular distance from the centroid, you have no lever arm. And no lever arm means zero twist. The object is simply going to translate and slide forward. Finally, Section 5, Exam Summary and Tips. Your textbook explicitly highlights this, and I can't stress it enough. Visualize the forces and moments in 3 dimensions. You simply cannot blindly plug numbers into equations in statics. You have to reflect, look at the geometry, and mentally animate how those forces are attempting to twist the structure before you ever pick up your calculator.
If you can master that simple lever concept and visualize it perfectly in 3D space, absolutely no force moment problem is going to stump you. Just remember that lifting 20 kilograms with one finger relies on the exact same fundamental math as analyzing a 3D structural cube. Always verify where your forces are acting relative to the centroid and rigorously follow your procedural steps.
I'll leave you with this final thought. Now that you can perfectly balance these forces and command the mechanics of rotation, what incredible systems will you go on to build? Thanks so much for joining this explainer, and good luck engineering the structures of tomorrow.